profile still that normally is done in our lab. Okay, so what are the other features that you can generate? What are the other means you can perform machining operations that you can perform in a milling machines? Let us see that. In a milling machine, you can also perform drilling operation by using specific type of tools. There are specific cutting tools for each type of operations. You can make a slot, you can make a V groove. Okay, and any type of profile that you require. Suppose you require some specific profile which is some curve type of feature is there, so we have to use a specific type of tool for that, known as form tool, which just gives that kind of geometry. Basically, if you see closely, the type of design that is formed over the workpiece due to machining operation is just the opposite replica of the cutting tool, basically of the profile of the cutting tool. You will observe that. Okay, so let us now get into detail about the machine tool. Yeah, so there are different types of milling machine tool that is available. The most used are vertical milling machine, and another type is horizontal milling machine is also there, that I will be dealing with that later on. So if you look at this vertical milling machine, why it is called vertical? Okay, first let us go into detail about that. Now, if you see closely to the machine, you have got this particular head. Okay, there is a driver where the driver motor is installed at the top. That means this gives the rotatory motions. Okay, and here is a spindle where you attach your cutting tool. Now, in this case, the cutting tool is called end milling cutter, basically. Okay, so end milling cutter, if you do not recognize it, so it will look like just like a drilling machine, drill bit. Okay, you might have observed drill bit at your home or in the workshop. So it looks just like a drill bit, but there is slight difference. Okay, so you have to fix this particular tool over here in the vertical positions. Okay, and this will give a rotatory motion with the help of motor. Okay, so the tool is fixed vertically and it is rotating about its axis. Now, where to fix the job now? So you can see there is a work table out here. Okay, so you have to fix your job over here by the help of some kind of fixtures or attachment, which will hold the job firmly onto this work table. Okay, now here the workpiece shouldn't have any motion. Okay, like with respect to this work table, it should not have any relative motion with respect to work table. It should along with the movement of the work table. Okay, that means it should be means fixed firmly by any kind of you know uh, fixtures. Okay, now you can ask a question. Okay, I have fixed the tool over here, I have fixed the job. Now how do I just connect this tool so that there is a continuous attachment between the continuous relative motions and an intimate contact between the cutting tool and the workpiece? Otherwise there will be no real machining. Okay, so we need to move the work table in that respect. Okay, so how do we move this work table? Now if you observe clearly, so you will notice a handle over here and another hand wheel over here also. Okay, so by rotating, giving a motion clockwise or anti-clockwise, it will move the work table in a linear direction. If we take towards the right as x directions, though it will move positive x and negative x directions if you operate on these handles. Okay, clockwise or anti-clockwise respectively. Now, the work table can also move inside, means in this directions. If you take this as a y direction, so the positive y, negative y, it can move by the help of this hand wheel. Okay. Another, it can move in the vertical directions also, so as to engage with the cutting tool. So in the z direction also there is a particular hand wheel which helps you to move it in a push it in a vertical directions. Okay. Now let us move on to the second type of the milling machine, which is looks a bit different. Okay, in how we attach the tool. So this is called a horizontal milling machine. Now, Now, as we have seen in the vertical milling machines, we are attaching the cutting tool in a vertical positions. Okay, and we are giving them a rotatory motions about its axis. Now, in this horizontal milling machines, what we do, we attach the cutting tool in this arbor. Okay, and this is in the horizontal axis it moves. Okay, so how it will move, this is also given a rotatory motion, but it rotates about the axis of the arbor, right? This is called arbor, where the cutting tool is fixed. How the cutting tool looks like, I'll show it to you. And similarly, the job is attached above this work table by help of any fixtures. If it is a round object, we will have a chuck, just like a 3-jaw or a 4-jaw chuck that is used in a lathe machine. Okay, and if we have a rectangular, suppose, object or any different type of geometry, we will have respective fixtures for that, and by the help of which we can attach it above the work table. And similarly, how to move the work table? It is same as the vertical milling machines. We have the hand wheel over at this end as well as at this end. If you can see, by giving a rotatory motion to this hand wheel, this work table moves in a x direction. See here, the directions are mentioned. So it can move in a positive x or negative x directions. And there is also a hand wheel to move the saddle. This is called a saddle basically, over which the work table has been placed. Okay, so it has got a guide ways, okay, over which the work table slides. Okay, so by help of this hand wheel, you can move this work table in a z direction, this positive z or negative z directions. Okay, there is another handle is there by help of which it can move in a vertical direction, in this case y direction. Okay, in a vertical directions, this table can be lifted. Okay, by help of this motions, you have to engage the workpiece with the rotating cutting tool, and thereby by relative motions and intimate contact, the machining operations is done. Okay, now care should be taken in this aspect while you are engaging the job with the tool, that you have to do it with that very slowly, because if you try to do it in a hurry, what will happen, when the cutting tool will engage with the workpiece, there will be a sudden jerk, okay, a sudden opposing force on the cutting tool, rotating cutting tool, and this might damage the cutting, okay, as well as the workpiece. Now workpiece might be of least expensive material also, so if we have any problem with the workpiece, okay, we can change it. But if we have any permanent damage to the cutting tool, that becomes a workpiece. Okay, general cutting, because a cutting tool, it is very difficult to manufacture and give that particular shape. Okay, so care must be taken so that we don't damage the cutting tool. Okay, that is our priority. So in that aspect, we will have to engage the job at a very slower rate towards the at a acceptable speed, that is called as a feed motion. Okay, at an acceptable feed motion towards the, while engaging towards the cutting tool. Okay, now okay, let us first show you how the cutting tool looks like, so that you will have a specific idea. Okay, so these are the various milling operations that is performed using different type of milling cutters. Okay, so if you look closely over here, there are different shapes of the milling cutters. Okay, uh, and when the milling operations is performed, you can see it will give a replica, an opposite replica of this milling cutter. Okay, so how will the job look like after it is machined? Let me show you so that you will have an idea. So suppose, let us take this milling side milling cutter. Okay, when the milling operation is finished, how will the work look like? It will look like this. Yeah, so this part is machined off. Okay, this part is machined off. So what it is showing, that it is having somewhat a replica of this, negative replica of this. So basically, whatever feature that you need to make, you need to have a particular machine tool with respect to that. Okay, So there are different type of machine tools that is there. This is the space milling cutter is there. Let me show you the other machine tools. Yeah, there's other milling cutters. So as you see, there are different types of shapes that is there. One is the slab milling cutter, which is mainly used to generate a flat kind of surface, a larger flat surface. Okay, so it has got a helical kind of cutter. Okay, teeth. These each of this cutter teeth, it is known as teeth. Okay, just like you have teeth in your mouth, so which bites with the help of which you bite the food. Similarly, in this cutter helps in biting the workpiece, okay, and machining it, okay, by the help of this multiple cutting edges. So these are called as a teeth. That is why this milling cutters is known as a multi-point cutting tool. Why? Because it has got multiple cutting edges, okay, with which the machining operations is being done, okay, which is different from that of the lathe machine, which where you use just one face of the cutting tool. It has got just one cutting edge, okay. So this is the difference. So here you can see this is get we by the help of this we can make a slot, we can make a v-shaped groove as well, okay. So here we can make a v-shaped groove by using this type of cutting tool. We can make an angular kind of feature, okay. We can even make a circular type of groove or a circular kind of profile by using this kind of form tool. These are basically known as form tool, to get a specific type of geometry, okay. So now, as you have understood how the cutter looks like, now we will go into the basic working principle. Okay, so this is just a schematic diagram of the horizontal milling machines in a simplistic way. It has been shown. So here is the cutter. This is basically you will work upon face and side milling cutter you will be using. So it has been fixed onto the arbor, and this is given a rotatory motion, okay, about this axis, about the arbor axis, and it rotates. It can rotate either clockwise or anti-clockwise, how we wish to, okay. uh, and here is the the saddle or the, and this is the work table over which the object has been placed onto a fixture, okay, where it tightly holds the workpiece so that it doesn't move out, okay. And we slowly we raise this column, we raise this knee, okay, in a vertical motions by the help of some handle. And we can also give an x and y directions as I have told in the previous slide. And therefore this is the way that you can slowly engage the workpiece with the cutter tool, okay. Now there are different type of specific way the cutting can be obtained. As I have told, the cutter can be given either a clockwise motion or an anti-clockwise motion. So in that aspect we will have a different type of cutting experience, okay. So let us see both of them. So, with respect to the workpiece motion or the job motion and the cutter motion, there are two specific types in which milling can be performed. Okay, so let us take this workpiece, and this cutter is moving, suppose in an anti-clockwise directions. Let us take, okay, and the workpiece is fed towards the towards the tool. Okay, see the feed directions is given over here. Okay, feed is basically the motion that is being imparted to the workpiece. Okay, the horizontal motion to say. Okay, and while it engages with the workpiece with the tool, see how the cutting motion is being obtained. So let us take, for example, this cutter tooth. Okay, this specific. Let us ignore this part. Let us be means observe this one. So while it is going above, means this is having an anti-clockwise motion. So it will, this tooth will move upward.
Sir, your mic is
Sir, your voice is not coming, sir.
Sir, you are
Sir,
not
you're not
audible.
audible.
Okay, I don't know.
Excuse me, sir. Somebody is excluding me from the meeting and deliberately removing me out.
Same thing happened to me. It's some technical error. So leave the meeting and then join again. It should go.
yeah
happened
happened
with
with
me too.
Me too.
Hello, can you hear me now?
Yes, sir.
Yes, sir.
Yes,
Okay.
sir.
Where did you last
Yes, sir.
hear my lecture? Is at what part you stopped?
That was
Sir,
moving in anti-clockwise direction.
Okay, fine.
So you have
Okay,
said
fine. You please switch off your microphone so that you can hear clearly. Okay.
Sir, but there is some problem. I don't know, but some of us are getting removed deliberately.
Okay, that might be due to the network issue. Okay, please check
Sir,
your
I
network.
Yes,
can,
sir. Even I
I
got
can just
removed.
leave
Sir,
and then
somebody
join
is
again. It
Okay,
should
fine,
go.
fine.
excluding us
Please
every
keep
time, and
quiet.
I am getting somebody is removing me from the meeting every time.
Okay, that you can handle. I cannot do anything from you. Okay, please listen to the lecture as long as you are here. Okay, otherwise it will be problematic for all of you. Okay, so please listen carefully while in the lecture. Don't create any kind of commotion over here. Okay, so we were discussing the upmilling cutter. Okay, how the upmilling operations is being done. So as the cutter is rotated anti-clockwise direction and it is engaged with the workpiece, what happens? Let us concentrate on this particular tooth of the this cutting tool. And while it moves upwards, it tries to chip off a part of the workpiece out in the form of chips. Okay. So while it is moving up, you can observe that gradually it is digging into the workpiece. Okay, so the thickness of the chip is varying from this particular end to this particular end. It is gradually increasing while in moving in the upward directions. So basically the cutting operations is being done while the cutting tooth is moving upward, right? So this is the reason why it is called upmilling. Okay, so you have got it why it is called upmilling. Right. Now you have to look at another thing as well, that in this case, the motion, relative motion between the tool and the workpiece is opposite. That means when the feed motion is given in the left directions, the cutter motion is in the, if you take this particular point, instantaneous point, you will observe the cutter motion is towards the right. Okay, so it is just opposite in directions. Now let us see another thing, terminology in this. So what is the depth of cut basically? Okay, so in this aspect, how much depth, up to how much depth the cutting tool is digging into the workpiece and it is chipping away, it is removing the material, is called depth of cut. See, it is denoted by small d. This is this particular distance. Let me point it out more specifically, this particular distance. Okay. So you have understood why it is called upmilling and how the operations, the relative motion between the workpiece and the cutter is working. Okay. Now the second type of operation that can be done is called downmilling. It is just the opposite case of upmilling. So by meaning of opposite case, you might have understood that, okay, so the cutting might be in the downward direction. Yes, of course, the cutting is actually in the downward directions. So how is it? In this case, let us take the workpiece is moving in the similar direction as the previous one towards the left side. It is being fed at the left side. Okay, and while the cutter is being given a clockwise motion in this case. Okay, so while it is engaging with the workpiece, if we see the cutter is engaging or tooth is engaging over here, let us concentrate on this particular tooth of the cutter. The cutter is engaging at the top and it is gradually coming down while removing a piece of material out of it. So the maximum thickness of the chip that is being formed is over here. Okay, it has got a maximum thickness. And while it is going down, the thickness of the chip is gradually reducing. Okay, and another thing is that the motion, the relative motion between the the workpiece at this particular instantaneous position is similar in directions to the workpiece motion. That means the feed motions. Okay, towards the left, as the workpiece is being given a feed motion towards the left side. At this particular position, if you observe, okay, instantaneous position, then the cutter is also being moved in the leftward directions. Means I mean to say this particular motion of the tooth, if you take at this particular instantaneous positions. Okay. Now here also similarly, the depth of cut you have understood it is same as this one. There is no big difference. Okay. So this is specifically the difference between the up milling and down. Okay. In both way we can cut the job. Okay. Now here the up milling is called conventional milling technique. Okay. If you want to write it down, sir. This is called conventional method of milling. Okay. Now, there are specific advantages and disadvantages of both of them, but you need not to go into that detail. Okay, it generally varies on what type of particular. If you somebody asks that what particular type of milling technique we will apply. So it basically depends upon what type of milling cutter you're using and what type of workpiece you are using. That depending upon the hardness of the workpiece. Basically, because workpiece are of various types of hardness. If you take mild steel, it is relatively soft. If you take suppose a forged item means which has undergone forging process. Okay, so it makes it quite hard. Okay, so if you take harder object, it becomes very difficult in the case of down milling tool. It might damage the tool. Now one might ask why? Why on earth is that? That it might damage the tool. Okay, so if you observe closely, so at this particular point, while the tooth is engaging to the workpiece, it will experience a sudden jerk upwards. Okay, while it is engaging because there is a sudden impact of the cutting tool with the workpiece at the top surface. Okay, while if you see over here, there's a gradual force, opposing force. So basically over here, this cutting tool is experiencing very less cutting opposing force, while this is experiencing a sudden opposing force. So when dealing with a very hard workpiece like any kind of forged item or a nickel item, nickel metal, okay, which has got a very high hardness or a high strength steel. So in that aspect, it might bring permanent damage to the cutting tool, and it might break. Cutting tool might break. So in that case, we will adopt up milling technique. Okay, but while when your workpiece is very soft and very ductile in nature, okay, and your cutter is quite tougher in that aspect, okay, and your cutting tool is not brittle in nature, then we can go for down milling operations without any problem. Okay, now there is another difference between these two. If you observe closely, that while this in case of up milling, while the cutter is moving in anti-clockwise directions, you will feel as if the cutting motion or the force is upward. Okay, the force with respect to the workpiece is upward. Okay, that means this cutter while cutting, it is somewhat pulling the workpiece upwards. So you need to have a proper fixture for holding the workpiece. That means the workpiece should be held very firmly onto the work table. Otherwise, while in the cutting motion, while machining, it might dislodge the workpiece, and it might, bring damage to the cutting tool as well as permanent damage to the workpiece as well. Okay, if you don't understand this one, so in a easy aspect, you can imagine like you have been given a block of butter and you have a spoon. Your mother tells you, okay, give me a spoon of butter. Okay, so if you take out butter, scoop out butter in this way, you will observe that the block of butter is pulling off of your hand. Okay, so you can try out even while having breakfast tomorrow. Okay, that which way is easy and what is the force that is coming out. So when you will scoop out butter in the upmilling type of technique, you will see that you have to hold the butter block firmly on your hand. Okay, while in the downmilling operations, there is no such thing. Okay, because you're scooping out the piece of butter with the help of spoon in a downward direction, so you will feel okay, you can hold the butter block very firmly on your hand without any problem. Okay, so with respect to that, in that aspect, upmilling is a bit tough. Okay, because you need to have a very good fixture for holding the workpiece. So there are advantages, disadvantages in both aspects. Okay, so the operator usually decides which type of milling operations he wishes to carry on, depending upon his machine condition, depending upon what type of workpiece he has to machine, depending upon what type of cutting tool he is using. And while with his experience, he will decide what type of machining operations he will carry. Okay, I hope so. This part is a bit clear now.
Sir, I
Okay.
have doubts.
Yeah, please go ahead.
Sir, why the length of chip is how it is getting reduced?
In reduce in case of downmill, right?
Yes.
Okay. Please see here. Suppose take this as a instantaneous positions. Okay. Now, when the cutter, in this particular tooth of the cutter is gradually moving down while cutting, you will see that this particular chip, this thickness will gradually reduce. Okay, it does reduce. Okay, you will observe. Okay, while in this case it will gradually increase. Okay, because you have not gone through the particular lab, and okay, so you will not observe this, but this particular variations in the chip thickness does occur. Okay, while you are scooping out a particular material. Okay, with this particular kind of cutting tool. Okay. So
Yes.
is it clear now?
Sir,
Yes.
Yeah,
so excuse me,
go
sir.
ahead one by one.
What are the advantages of downmilling over upmilling?
Yeah, so in case of downweighing, one thing I have told that there is no problem about holding the job because the force is downward in downweighing operations. Okay, so the problem which you are facing in the case of upweighing, like you have to hold the workpiece really strong with a good fixture, that is not a big deal of problem over here in downweighing. Okay, so that is one advantage is in this aspect, and the surface finish is also good. Okay, in case of downweighing, whereas there are advantages and disadvantages as well in this, like there is a problem of tooth breakage when dealing with very hard kind of workpiece. Okay, so it upmilling has also got its own advantages, like when you're chipping away material, the chip normally flies away, means in opposite direction to the finished part, because this is the finished part of the workpiece. So while this machining operations is being done, the chip is thrown in opposite direction, while in this part, in case of downweighing, the chip is thrown in the finished part direction. So there is a possibility of scratch in the finished part as well. So there are respective advantages and disadvantages in both aspects. Okay. Okay. Did you get it now?
Sir,
Yes,
Sir,
sir.
in case of
So,
sir,
actually,
Yeah.
in
I
case
have
of
one.
upmilling,
which one is the
thickness of
One by one, one by one. I could
sir,
not
which
hear.
one is the
Which one is
conventional method you said?
Conventional is upmilling. Upmilling is called conventional milling.
Okay, sir.
sir? Which one is more required energy, sir?
Which one is more required?
Energy.
Hello.
Energy. Okay.
Consume, sir.
So the upmilling requires more energy. Okay. Basically, why it requires more energy? Because while cutting, if you see at this point of time, at this particular instantaneous point, there is almost no opposing force. But while it is gradually, going in the upward direction, the opposing force keeps on increasing, keeps on increasing. Okay. So if you take the net force requirement or the power consumption in case of upmilling is more. Okay, almost about 5 to 10% more than with respect to downmilling. Yeah.
So in case of
Any
upmilling, thickness
yeah,
of
in
chip
case
gradually increases or decreases.
gradually increases. It is just the
At the
opposite of
top,
down.
thick. At the top,
So yes, I couldn't hear it properly. Please repeat.
at the top thickness much more.
Yeah. So in the case of upmilling, see over here, the thickness is almost minimal, close to zero. So while it is gradually moving up, the thickness keeps on increasing. So obviously you will have a chip formations where the thickness over here is low and over here it is more. Okay. Now, if you analyze both type of chips with your hand after the machining is over, then you will not be able to recognize it because it will look similar. Okay, but while in the machining operations, you can observe that how the chip, thickness varies. Okay, so in case of upmilling, it gradually increases over here, and in case of downmilling, with respect to the top, it gradually decreases the chip thickness. And these chips are in the shape called as curet trochoids. Okay, you might right. You don't require also. Okay, any other problem?
Sir,
In
Sir,
both
can
it's
sir
similar
with
to
the feed workpiece also will move left side, sir.
Yeah, workpiece is given the feed motion.
Sir,
I have
if
told that the workpiece is fixed above the work table, and there are two handles to operate to move the work table in a x direction, positive x, negative x directions. Okay, that particular slide. Yeah, you can observe that there is a hand wheel. We are
yes,
positioning
sir.
the workpiece over here. So
Yes, sir.
the feed motion is given in the x and positive x direction or negative x direction, whichever with respect to the workpiece, with respect to the cutting tool. So by rotating this hand wheel over here, you can give the feed motion.
Sir,
Got it?
in the time of work, we should rotate that, sir, continuously to move left
Which
and
one?
right.
Yeah. The hand wheel you should rotate it. Yeah, manually. And if it is automatic machine, then there might be automatic movement also.
Sir, can you please explain how downmilling damages the work machine?
Damages the cutting tool, not the machine.
Yes, sir. Yes, sir. Cutting.
Yeah.
Sorry.
Okay, I'm explaining again. See, while in this motion, while the cutting tool is given a downward motion, if you observe closely, at this point, there is a sudden, a sudden striking of the cutting tool teeth, top surface of the workpiece. Now here, as there is maximum amount of chips, so there is maximum amount of opposing force as well. So this
Okay,
will
sir. I
act
got
as
it.
an impact loading upwards.
Yes, sir.
Okay. While in case of upmilling, you see there is almost zero opposing force. Although there will be practical due to friction, there will not be zero at all. Okay, there will be some point, some opposing force, but with respect to downwilling, it is almost negligible. Okay, understood?
sir,
Thank you,
Can
sir.
you
Thank
comment on the number of rotations we require for completing a given job in upmilling and
There
downmilling?
is no
Will you be
specific that kind of rotations. It is being given a constant RPM. The tool rotates at a constant RPM, given RPM. Okay, and the feed motions is independent to this RPM basically. Okay, so the feed motion is being given manually. Okay, so there is no specific RPM that you require. Okay, to be given. There is no specific number of rotations that you require to complete a particular, machine a particular length of job. Okay, it is being given a constant RPM with the help of motor. Okay.
okay,
sir, what's the
Cutter, sir.
different in
Yes, difference in
positioning of the workpiece in horizontal milling machine?
yeah. See, if you can see the schematic diagram, this is the arbor. So the cutter is basically mounted in this way. Okay. Can you see it? So the
Yes, sir.
rotation of the cutter is about the
Yes, sir.
axis of this arbor, right?
Yes.
This is basically a side view, which is called. Okay, if you stand over here and you try to look in this side, you will see a full circle cutter. Okay, but if you are seeing from this aspect towards the work table handle aspect, I mean in this position you are standing, then you can see just this space of the cutter. Okay, it is
Yes.
basically a round cutter. Okay, so now you
Sir,
get
which
it.
one is fast cutter?
Which one is
Fast cutter.
fast cutter? I didn't get your question. And it means you mean to tell which one cuts fast, machines fast.
Yes. Yes.
It depends
Yes, sir.
completely on what is the being given and what is the RPM. Okay, it anyone might be slow, anyone might be fast. There is nothing like that. Which one cuts fast? Both of them can cut at the same. Okay,
Sir,
it
in the
completely depends how
downmilling,
much speed. Okay, the mood, yeah, I will deal with the problems later on. Let me finish it first. Okay, you will look at the video that will be shown, and by looking at the video, it will be much more clear. Okay, and by the end, I'll give you time, okay, for asking the questions, and then I will, give your answers. Okay, first let me complete this, otherwise we will be stuck over here. Okay. Okay, now the milling calculations basically that is required. One is the cutting speed. Okay, cutting speed in meters per minute. Okay, so basically I have told that the milling cutter is given, the motion in RPM, or revolutions per minute. Okay, and the cutter has got a specific diameter. Okay, so now if you try to find out the cutting speed in meters per minute, so this is the formula. These are basically formulas. It is available everywhere. Okay, so by this formula you can obtain the cutting speed. Not much of a big deal. Okay, now here you can, if cutting speed is given in meters per minute, you can find out the RPM by this equation only, just by rearranging it. Okay, now another is a feed motion of the workpiece that is there. Okay, so this is the feed motions in, you can say, millimeters per minute. It has got a dimensions, and this is basically the RPM of the cutter, and this FZ is the feet per tooth. That means how much the workpiece is moving with respect to per cutting tooth, how much distance it is moving. Okay, and this Z is the number of cutting edges, or the number of tooths in the milling cutter that is there. And just changing it, you will get the feet per tooth as well. Just it is the same equation, just rearrange it. Nothing different. Okay. Now let us come to the most important part. Please listen carefully, otherwise it will go above your head. Okay. Now, what is basically indexing? What is the meaning of indexing? First of all, let us come into that. Indexing basically means that if you're given a circular kind of object, okay, how can you divide that particular circumference into equal number of parts, equal number of edges? Okay, how can you do that? Means, I mean to say, equal means equal length. Okay, means if somebody asks you, okay, try to make a part, okay, reshape the circular periphery of a cylindrical job in such a manner that there are 6 sides or 10 sides, whatever. Now you have to make sure that all these 10 sides or 6 sides, which one is required, is of equal shape. Now how you are going to ensure that part? Okay, so there must be some way by help of which you can ensure that, okay, every edges that I obtain is exactly of same shape. Okay, you have to ensure that particular thing. Now how you will do that? Okay, if somebody, now you may ask a question that, okay, if somebody asks me to do a 4-sided part, okay, it is comparatively easy. You might say that, yeah, that okay, fine, if somebody gives me a cylindrical job, what I will do, I'll just with the help of a dial or something, where I will divide it at equal divisions. Okay, and by the help of which we can easily cut the part into equal shapes. Now how you will do that? Suppose somebody so in a complete 360 degrees, okay, you will divide by the number of sides that you require. Okay, like suppose you want to have a 4-sided object. Okay, so there is complete 360 degree in a particular circle. Okay, so if you require a 4-sided object, you will divide it by 360 by 4, so it comes out to be 90 degree. That means you need to rotate the workpiece from the first position by 90 degrees so as to machine the second part. Okay, second edge. Okay, after machining the first edge at the first positions, after machining is over, then so as to machine the second side, you have to rotate the workpiece by 90 degrees. So, okay, by this kind of dial, it is very easy to obtain. Okay, you will just have to rotate it by 90 degrees. This is 90 degrees. Yeah, you can easily mark and rotate it. Okay, so you can feel that, okay, it is very simple, not a big deal. Okay, but it becomes a problem when you're asked to deal with a number of sides of very large magnitude. Like suppose 40, 50, 60. Okay, and it becomes more problematic when there is a odd number. Okay, so in case of odd number, what will happen? Basically, what happens? You need to ensure that you have a resolution almost close to 1 degree or lesser than 1 degree. So reaching a resolution close to 1 degree or less than 1 degree is very difficult. Okay, by manual operations. So you need to have an alternative to that, so that it can ensure the proper indexing or proper, you can say, length of each divisions. So in to ensure that, there is a particular type of attachment that has been fixed into the milling machine called as the indexing plate. So this figure what you're seeing is basically indexing plate. Okay, so it has, as you see, it has got number of holes to it. Okay, so what does this holes do? Okay, what is the purpose of this? Okay, I'll be explaining what is the hole, what is the use of this, basically holes in the indexing plate. So as you can see, there are different types of indexing methods which are available. One is called direct indexing. It is exactly similar to what I've explained just now. Like you have a dial and you can rotate it by that many degrees that you require, and it works fairly well when the number of sides is pretty low. So in that, what happened? How it's done basically in a milling machine? You cannot attach a dial over there. So there is a dial which is already given in that machine. Okay, if you see this index head spindle over there, already permanent divisions are made in which you can rotate directly the workpiece and get it. So this particular, the entire thing is called a dividing head. Okay, let me explain the parts of this first of all. So this is full is called the dividing head. Now what are the components of the dividing head? This, as you can see, it is similar to this one. Okay, it is called as an indexing plate, which has got a number of holes at different particular radii. Now while you are going outward into higher radii, you will see the number of holes are changing. Okay, it is increasing. Okay, so there are basically three types of indexing plates available, and these are the number of holes at particular radii. Okay, at different radii. Okay, so, and you have got a crank, index crank, which helps you to locate the particular hole, and there is a indexing pin where, with the help of which you can lock into one of the holes. Okay, now why to do that? I'll be explaining it. Okay, so here you can see a shaft is connected. Okay, right from here, and which has got a spiral kind of feature, a screw kind of thing over at this end. Okay, this is called worm. Okay, this screw kind of feature which is on the shaft is called worm. Okay, and the type of gear that you're looking, which is attached to this kind of worm, is called a worm wheel. Now, basically, in a milling machine, usually there are 40 number of teeth in this worm wheel. Okay, and there is a index head spindle at the back of it. Now, if you extend this, particular thing, suppose there is a shaft over here. Okay, and this is directly connected to the fixture where your job is being held. Suppose you have a circular job, mainly a circular job you have, so it is generally held by a chuck, right? So this particular thing is coaxially attached with that chuck, so that if you rotate this particular indexing crank, it will give rotation to this shaft, and thereby it will also rotate this worm wheel, and thereby it will impart rotation to the workpiece. So simply by rotating this indexing crank, you will impart rotation to the workpiece. Now somebody might ask that, okay, if I rotate this handle by one complete revolution, will it bring one complete revolution of the workpiece? No, the answer is no, because while this worm and worm wheel is engaged, so it reduces the number of revolutions of the workpiece basically while it is engaged. So when this one complete revolution, when this indexing crank is revolved by 1 degree, or 1 degree means one complete revolution, then brought back to the same initial positions, the shaft is rotated in a similar way by one complete revolution. But this worm wheel is rotated just by 1 teeth distance. 1 teeth distance means the distance between 1 teeth. It means 2 consecutive teeth. Okay. So there are 40 number of teeth. So you need to have you have to do 40 number of revolutions of the indexing crank so that this worm wheel comes back to its original positions. And therefore, similarly, the amount of rotations which is imparted to this worm wheel is also imparted to the workpiece. So if we give 40 number of revolutions of the indexing crank, the job that is fixed above the work table with the help of a chuck is also rotated by 1 complete revolutions. So 40 revolutions is reduced to 1 complete revolutions of the workpiece. Okay. Now let us take now let us first understand what is direct indexing now, how to do that. Now, what happens in case of direct indexing? Direct means we will
Hello,
move the
sir.
workpiece direct. Yes.
Sir, what does worm single thread do?
Yeah, one single thread
Worm
loop.
sing.
That is reducing the number of revolution that is imparted to the worm wheel. Okay, it drastically reduces the
Sir,
rotations.
where
Okay.
is the workpiece?
Whereas the workpiece is not shown over here. Basically, if you see this worm wheel, workpiece is attached coaxially to it. Okay, this is just one part. Okay, the workpiece is attached with the help of chuck, which is aligned coaxially with this worm wheel axis. There's a shaft actually. Okay, which by the help of which it is attached coaxially somewhere here. Okay, and this can be in the vertical directions. Okay, you will see it in the video. Okay, and then you can
Sir,
understand properly. Yes.
sir, if worm shot rotates, then how the
Mhm.
worm will also rotate, sir? It's in
Because
the
it
up.
is attached.
Yeah.
Yeah, because it has got a contact with the worm wheel, means with the worm.
But
It has
the
the worm
axis is not same, no, sir.
whatever
The
it is
axis,
not same.
the
If
axis
axis
of
is
worm
not
shaft is
same,
XM.
still it will rotate. Okay. Now you just imagine this is just a screw kind of feature. Okay, and this is a toothed kind of feature. When it is perfectly fixed onto this one, okay, if you bring rotation to the shaft, it will always rotate this particular wheel. Okay, due to this motion, you just imagine. Okay, you imagine it. Okay, you will understand. Suppose think that there is a shaft which has got a spiral end edge to it. Okay, a portion to it, and over which the toothed kind of gear is mounted, and try to rotate the shaft. You will observe in your imagination that it is going to rotate. It will rotate. Okay.
Sir, the worm shaft will be moved left and right, sir. If
No. It will giving a
it
circular
will be
rotation.
fixed,
Yeah,
it
it will
will
be
be
fixed
fixed
over
itself.
here. It will just move in a circular. It will be given an RPM. RPM means revolution basically.
Yes, sir.
Okay, when the indexing crank is revolved, so as it is fixed with the shaft by this nut, by this lock nut, it will also means revolve basically. Okay, let's see. It will also revolve like, okay, and this will accordingly it will revolve like this one. Okay, understood?
Yes,
Okay,
sir.
indexing crank is moved like this, or it can move in the opposite way. No problem.
Sir,
Okay, now what? Yeah.
sir, I didn't understand the importance of warm single thread. Can you explain it?
Yeah, the worm single thread, what it does is basically this worm single thread helps in transferring the rotatory motion to this worm wheel, which in turn rotates the workpiece. Okay.
Sir, why we
As
can
now
only
another
rotate
thing,
it?
as the motion that has to be imparted in vertically in 90 degrees. See, the worm wheel rotates in this direction, but the actual motion that has to be imparted is in this direction. Okay, so how can you do that? Okay, so and also you have to reduce the number of revolution that is imparted finally to the worm. So we can only do it by worm single thread. Single thread is different thing. Okay, now by worm actually you can do that. Okay, let us now understand how you will do direct indexing at first. Okay, otherwise time is passing away. Okay. So basically what happens, there is a locking lever over here, which is attached to this shaft. Okay. So as you know, my means of direct, what it is meaning, that means you have to directly, rotate the workpiece, and that means the motion of the workpiece has to be independent of the motion of this indexing crank. Okay, that means if we want to do it independent motion, then obviously we need to disengage this particular portion. So there is a lever at this end or at this end. Okay, by the help of which, by unlocking that, what will happen, this particular shaft will move down. Okay, this particular shaft will be pushed down, and therefore what will happen, there will be a gap that is created over here. So in that way, there is no contact between the worm wheel and the worm. So the motion of the motion of the shaft will not bring any further motion onto the this worm wheel, right? Because it has become independent now. Okay, now what we do, how to rotate the workpiece then? Now the role comes of the indexing head spindle. So the back of this one, it is basically a, wait, yeah. So the indexing spindle is just like a circular one. This, assume this is a circle. So it has got a permanent divisions made to it. Okay, in the range of 4, 6, till 24 normally it is there. So already divisions has been made. So if you require lesser number of sides, you can directly do it from this thing. So if you need 4 number of divisions, you can accordingly turn this indexing head. Okay, and there is a pointer also fixed to it. Okay, so that you can easily ensure that the number of sides that you require is you can get it, and also the sides are of equal length. Okay, now the main portion that you will be dealing is the simple or plain indexing. Okay, simple or plain indexing is that the motion of this indexing crank will bring about a motion of this worm wheel because of this joining. Okay, now in this case, the shaft will be attached to this worm wheel. Okay, so any motion that is brought about by the indexing crank will bring about a motion on this worm wheel and thereby to the workpiece. Okay, so what we do, suppose you are given a job to make 4 side and 6 side. Okay, so what you will do? Suppose you are required to give and make 4 jobs, 4-sided job, for example. So as you can assume that there are 40 number of teeth. So 40 complete revolutions will bring 1 complete revolution to the workpiece. Okay, so if you require 4-sided, so it has to move by 90 degrees, right? So what you need to do is basically you need to divide the number of teeth available in the worm wheel, that is 40, by the number of sides that you require. Suppose you require 4 sides. Okay, so the result will be 10. Now what is this 10? Okay, this 10 is actually the number of revolutions that you need to make of this index crank. Okay, that means if you give 10 motions, okay, let us take it in the angular perspective also. So in a complete revolution, there is 360 degrees. Okay, so 360 degrees when divided by 4, it gives 90 degrees. Okay, so when when the indexing crank is revolved by 10 complete revolutions and it is brought back to its original positions, then the workpiece will move by an angle of 90 degrees. Okay, and similarly, when you require, suppose, a 6-sided object, let us take a 6-sided object. So what you will do, you will similarly, you will divide the number of teeth that is available in the worm wheel by the number of sides that is required, that is 6, which gives you 6 2 by 3, right? Now 6 revolutions is okay, you can give 6 complete revolutions. Now what to do with this 2 by 3? Okay, now here comes the role of the number of holes which is there in the indexing plate. So what I've told previously, that there are numerous number of holes at a particular at different radii. So okay, so indexing, this index pin suppose has been fixed to a particular radii which has got a 33 hole. Let us take it has got a 33 hole. So what you will do basically, you will have to multiply this fractional part with the number of holes which is positioned at a particular radii. Suppose there are 33 holes. There are specifically 33 holes in the indexing plate. Okay, so it will cancel out. It will give 11, right? So the result comes out to be 6 complete revolutions and 22 number of holes. Okay, this is in revolutions, and this is the number of holes after completing the 6 complete revolutions. 22 is the number of holes by which you need to move this indexing pin and lock it. Okay, this is the number of holes that you need to move. So after completing the 6 complete revolutions, you'll come back to its original positions and you will move it by 22 number of holes and lock the pin, right? Then only the job will rotate by 60 degrees. Understood? This is in case of 6-sided. Okay, that you will be doing. Okay. Similarly, if there is a suppose a different number of sides. Okay, so there will be a different fractional part, part. So we will have to multiply with the number of holes. Okay, like with the help of which it will give a complete whole number. Okay, so you might ask that, okay, here we have fixed it at 33 holes. How can we just move it to a different radii and lock the indexing pin to a different radii and multiply with a different number? So as you see, there are 3 different plates, each having a different number of holes at different particular radii. So what you will do, you can see there is a lock nut over here. You will just have to loosen the lock nut and you have to locate the indexing pin at that particular radii which you require. Okay, to multiply with this fractional part and again lock this nut. Okay, and thereby you will be fixing the indexing pin at that particular radii. Now you can easily get a whole number by multiplying with a suitable multiplying factor, right? So this is the way that you have to do the plain indexing or the simple indexing. Okay, so apart from this two simple indexing, there are more complex type of indexing that is available also. Suppose now when you're given a suppose a whole number or an even number, okay, even number specifically, it is very easy for you to find it out because normally what happens, the result is in whole number. Okay, so it is very easy to apply. But what to do if you have a odd number? Okay, so or a prime number. In that case, it becomes very difficult to obtain because it is it will never be in the range of this number of holes which is available in 3 indexing plate. So in that perspective, how to obtain, you have to a certain cleverly is done specifically, and there is a compound indexing method and there is a differential indexing method which is carried out, which is beyond your syllabus level. It is generally taught in higher years of mechanical engineering. But to brief you in this aspect, what we do, like in simple indexing, we are just rotating this indexing crank and fixing at a particular hole that you require it. Okay, after completing a certain revolutions. Okay, in compound indexing, what we need to do after carrying out this particular role, that is by locating the indexing pin at a particular point, we need to also rotate this indexing plate either in the similar direction or in the opposite direction. Okay, so to get the final number of sides. Suppose in that case, what happens, the formula comes as, suppose the same number of teeth are there and you need to reach suppose n number of sides in that aspect. So what will happen, suppose the indexing pin is moved suppose by n number of holes. Okay, and there are at particular radii there are suppose n1 holes. Okay, and you have to move this indexing plate, and also there is another locking pin like this. Okay, So you have to move the indexing blade either in this direction or in this direction. Okay, so positive is for similar directions as to the rotation of the indexing crank, and negative is when rotated in the opposite direction. So suppose in that aspect you are rotating the indexing plate by n2 number of holes in either clockwise or anti-clockwise, and in that this particular locations there are suppose n2 number of holes. Okay, so this becomes the formula in that compound indexing. Well, this is beyond your syllabus. You don't need to get into much detail. Basically, just for a brief understanding, you have told you that this is generally adopted when you need to get some complex number of sides in or either odd or prime number. In differential indexing is also the same, but here you need to attach a gear arrangement by the help of which the index blade automatically rotates. Okay, so this is mainly done in a prime.
Direct
Yes.
indexing and simple indexing are only there.
Yes, yes.
In our
I got
syllabus,
here.
it's only
Yeah,
direct
only
indexing
simple
and
indexing.
simple plain
Yeah,
indexing.
you don't need to concentrate on compound indexing and differential indexing. Okay. Don't need to break.
And the direct direct indexing.
Yeah, direct
One and
indexing
two.
is very easy. I have told you. You might read only concentrate on simple indexing or plain indexing. This is important for you. Okay. No need to concentrate on other forms of indexing. Okay, as of now.
Can you
Sir,
please explain direct indexing once more?
Okay, I'll explain it later. Okay, first let me cover it up.
What
Yeah.
is sector arm?
Sector arm. Okay, so there is a just like you have a ruler, right? While you draw a line or something like that, so as to locate the particular line. Okay, so here the sector arm is that you need to move it and you need to lock it at this particular position so that you don't miss out, because all the holes look similar. Okay, so you might forget which hole to point. Okay, and where is the starting position? So I have to locate this particular thing. These sector arms are given. Okay, for helping you out. Okay, this is the job. Okay,
sir.
Yeah.
So why this indexing is used, sir? I mean, sorry.
So
Why this
Mahavar
indexing
is and you're asking who is Krishna? Okay, okay, fine. So indexing is basically the form in which you divide the periphery of a circular part into equal number of sides. Equal number of sides mean equal length of sides. Okay, suppose you are given a task.
Sir, I'm not asking that, sir. Sir, why
Then?
that was used? I mean, why to divide like that, sir?
Okay,
For which purpose?
So there are different kinds of use of this, because various machines or various manufacturing processes might require different side of object. It is not that you only require a circular object or a square object. Okay, like suppose take the example of gear. A gear has number of tooths. Suppose you are given the job to make this worm wheel, how you will do? Okay, it has got 40 number of divisions and each at equal intervals. How you will manufacture that? Okay, but these all cases, like this is the example that I've given you. In many cases, it requires to manufacture a circular part into number of equal divisions. Okay, so in this case, this indexing plate will be helpful. Okay, indexing method will be helpful. Generally, for manufacturing a gear for as some kind of application purpose, this milling method is generally not adopted. Okay, there are specific machines for manufacturing a gear. Okay, but in indexing also it can be done. Okay, but it is not as precise. Okay.
Yes. Okay.
Excuse me, sir.
Yeah.
Sir, I got the process of how the gear turns, but how does it cut it into equal parts? I did not quite get that. Can you please explain?
Okay, it will be more easy if you see the video. Okay, I'll just
Sir,
start.
I too didn't understand that part.
Which one?
So this same part, that how is it cutting like that?
Okay, I'll show it to you. It will be more clear when you watch the video. After that, if you have any problem, I'll clear it out. Okay.
Excuse me, sir.
Yeah.
Sir, when worm shaft rotate, then it will exert a force on worm wheel which is parallel to the axis of rotation of worm wheel, then how it
Yes,
will rotate, sir?
parallel to the axis of the worm shaft and tangential to the direction of the worm wheel periphery.
So axis of rotation of worm wheel and the force exerted by worm shaft is in the same direction, then torque will be zero, then how it will rotate, sir?
I'm explaining you. See, when this part is given a rotatory motion, as this tool is in contact with this spiral edge, it
Yes,
will
sir.
exert a motion. When this will rotate by clockwise, let us say, this edge will try to push this teeth in this particular direction and rightward direction. Okay, so thereby it will have a rotatory anticlockwise rotatory motion. Understood now?
So when
Sir,
shaft
but the
rotate, then it
friction is along the axis, no, sir.
Which one is along the axis?
The friction between those two surfaces will be along the
yes, sir.
axis of worm wheel, no,
Along
sir.
the axis of the shaft.
Axis of rotation of worm wheel, na, sir.
Axis of rotation of this worm. This is called worm. This is called worm wheel. This axis is like this. These two axes is perpendicular to each other.
Yes, sir.
Okay. The axis of the shaft and the axis of the worm wheel is not in same direction. It is in perpendicular direction.
So in the video, this part will be shown, sir.
This part is actually inside a box. You cannot see it. Okay.
Oh.
Okay. Okay. If
Okay,
you have
sir.
any problem, I'll explain it again. Just let me complete it. Okay. If you have any problem, I'll clear it out. Okay. Let us first complete. So this part I have explained for the simple indexing. It has got nothing. Just you need to divide it by the number of sides that is required. The 40 is the number of teeth, which is basically here. So here you can see in a zoomed image how this, this is meeting this worm. The worm wheel is tooth of the worm wheel is attached, or it is in contact with the worm. Okay. So the motion of this one, it will impart a in anticlockwise motion. Okay, so this worm wheel, as I've told, this has got 40 teeth. So you will divide this 40 with the number of sides that you require, and you will get the number of revolutions of this indexing crank accordingly. Okay, this already I have covered. Okay, now your job, your task to do.
So
So you
please
would have
go
done
to
it
previous slide
physically
one.
if you are in the campus, but as of now, you will be shown a video. Okay, so what is the task? Basically, you need to do two type of operations. One is the four-sided operations, means four-sided feature, and another is a six-sided feature. You need to machine a circular kind of object, face of the circular kind of object in such a way that you attain a four-sided feature and also a six-sided feature. Okay, so this is simple mathematics. Okay, you can draw it in your notebook if you like it. Okay, suppose you are given a cylindrical block of 30 millimeter in diameter, and you are asked to machine out the cylindrical part in such a manner that you have minimum material wastage. That means the edges of this square is just at the periphery of this circular kind of feature. Okay, so can you find out how much depth you require to inside the cutter, means how much material that you require to remove from its periphery, means how much depth that you need to enter? Can you find it out? I hope so. It is very easy to find it out by simple mathematics.
So
Simple
please repeat your
geometry.
question once more.
You are required to machine out a particular circular cylindrical block, face of the circular cylindrical block, in such a way that you get a four-sided object. Okay, such that you have minimum material wastage. That means the edges of these blocks are just at the circumference of this circular block, right? So can you find out the CD distance? I hope so. You can. It is not a
Yes.
big deal for you. You can
Yes,
find it
sir.
out easily.
Sir, it will be
Yeah,
radius
4.39.
into
Yes, yes, yeah. So the answer is 4.395. Okay. So this is basically the amount of distance by which the cutter needs to cut out this particular distance. This is the maximum distance. So the cutter needs to be oriented in over here, and it has to be moved along this direction. Okay, that is why we require this CD distance. Okay, similarly, for the case of hexagon also, you can find it out. This CD distance by simple geometry in a similar way, you can obtain that. Okay, so it comes out to be 2.01. Okay, now I will show you the video and please observe carefully how it is being done. Okay, and after that, if you have any kind of problem, you can ask me. Okay,
Sir,
yeah,
so does you have to make this hexagon and square by using index machine
yeah. I
or
couldn't
by
follow.
milling machine?
Yeah, what
So
do you
actually,
mean?
you have to do hexagon and square by using index machine or up
Yeah, by milling machine
up and
only you
down.
will manufacture the job, and by while doing that, you will have to use the indexing method because you need a perfectly similar length of sides. Okay, so you will have to use plain indexing or simple indexing process. Okay, okay. Now let us
Okay,
go
sir.
straight away into the video. Okay, without wasting any further time. Any sound?
No, sir.
No. Okay,
No, sir,
then
there is
I
no
will.
sound.
Okay, fine. I'll have to then again unshare my screen and then again I will have to log in again. Is it audible now?
No, sir.
I don't think so. Is it?
Sir, you muted the video, sir, I think.
Yes, sir, it is audible, sir.
It is audible.
Audible?
Yes, sir, it is
No,
audible.
sir. No, sir.
Are you sure?
No, sir.
No, sir, it is not
Sir,
audible.
increase its volume.
No, sir.
No, sir, it is not audible, sir.
Okay, fine.
Not
Sir,
audible, sir.
if the video is in
Okay,
YouTube, you can share the link in the chat box.
that will be shared to you, but at this point of time, you need to understand, right? Okay, let me try out again. There might be some issue.
No voice, sir.
Was there any volume?
No, sir.
No,
No,
sir.
sir.
No, sir.
Sir, I think the system audio sharing is paused. That's why we can't hear.
No. It is on. It is on. Was it audible now?
No, sir.
Yes, sir, it
No,
was
sir.
audible. Low volume, sir.
Sir, you muted the system from.
This
Sir, the system sounds is muted in the taskbar.
now is it audible?
Yes, sir, it was audible.
It is audible.
Yes, sir.
No. No, sir.
No, sir. It is not audible.
No, sir. No, sir. Not audible.
Okay, let me try out again.
Not audible, sir.
Just hold on for a moment. Can you hear now?
No, sir.
No, sir.
No, sir.
No, sir.
No,
There,
sir.
there
No, sir.
might be some problem in the
There
network.
is a mute option.
The voice is very slow, sir.
Okay. Okay, fine. If it is not audible, then I will explain it myself. Okay, how it is being done. Okay, you just watch the video, and I'll explain it. Okay. So let us start from the beginning. So this is the horizontal milling machine that is there. Okay. So this is the machine bed of the work table, and this is the machine arbor basically where the cutting tool has been fixed. So it can give clockwise or anti-clockwise motion. So by the help of this hand wheel, as I have shown you, you can move this particular work table in the X direction, and with the help of these levers, you can move it in the Y directions as well as Z directions. Okay, so you need to do this job. You have to make it a square type of feature, as I have told you previously. Okay, so you have already calculated the CD depth of cut. Okay, so now it will be shown how you will do it practically. Okay, how you will engage the workpiece with the tool. Okay, okay, now similarly, in the case of hexagon, this CD part you will have to remove it by machining, and you have already by calculations you have covered that you need to remove this 2.01 millimeter out of it. Okay, and similarly this will also be done. What we will do, we will convert a cylindrical block. One edge of it we will have to make a, see, this is a cylindrical block. Once one top part of it, we will make it a square, and the bottom we will make it a hexagon. Okay, after completing the square, we will have to means turn this upside down, and we will manufacture this hexagon. So this is how, by the help of chuck, this particular cylindrical portion is being fixed firmly onto the machine bed, and this is the dividing head actually, where all this worm shaft and worm wheel has been fixed. This is the indexing plate, and you can see this number of holes over here, and this is the indexing pin which is attached to one of the holes. Okay, and this is the indexing crank. So this is basically the inside part of the this dividing head that I've already explained to you. This one you cannot see because it is totally covered. So this is the basically the worm that and this is the worm wheel which has got a 40 teeth. So the relative motion between the two gives the ultimate motion of the this chuck or the workpiece on which the workpiece has been fixed. Okay. So here it is, they are showing that it has got 40 number of teeth on this particular worm wheel, and by rotation of this indexing crank, as I have told previously, 40 number of rotations will give one complete rotation of the worm wheel, and thereby one complete revolution of the workpiece. Okay, so now they are going to start the machine and do the respective machining process. So this is the locking pin I have told you, by help of which we can move this particular, move this particular pin, indexing pin at different radii. See how the rotation of this indexing crank is rotating the chuck. So here first we will produce a square. We will machine out this part to make a square particular kind of feature at the cross section. Okay, so they are explaining that by rotating this by 40 number of revolution, this will rotate by one complete rotation, as I've already explained. Okay, so this has started. This is the rotatory motion has been imparted to this cutting tool, and now how you will ensure that how much cutting depth you need to give. You have got that already calculated it, but from where? From this particular edge you need to go inside. Okay, so you need to make sure that this cutting tool is just touching this edge, particular edge. So they are seeing that if it is touching, then it will produce a feeble sound. Okay, by help of that you will know it, that okay, now I am at the periphery of this circumference of the particular circular job. After that they have moved back twist it by a particular distance. So here is the DRO basically, where they will input the amount of depth of cut that they need to go, that they need to impart. Okay, now with the help of this lever, basically what they are doing, they are trying to lift the work table so that there is some by the amount of which they will cut out the motion in the z direction. Basically means this part. If you can see this particular part, by lifting the table they will ensure this part amount of depth it will cut. Okay, now what has happened, they have moved this work table in a y direction, basically means towards the operator, and then they will engage the workpiece towards the cutter by this x motion in positive x direction of the work table. They have not shown here that. See, they will slowly move past the tool and it will start cutting. See, the intermittent chips are coming out, discontinuous chips are coming out. If you can see. So basically, this is the upmilling operation that they are doing. So by operating the hand wheel, what they are doing, they can move this workpiece in a x directions. Okay, x means in a linear direction of this work table, I mean to say. So one side, one face is over. Now we have to revolve it by 90 degrees. Okay, means the workpiece. So what we will do, we will have to do 10 complete revolutions of this indexing crank so that this revolves by 90 degrees, as I have shown previously, as I have explained previously. See. So this is the 10th revolution. Now again they will engage the pin at its initial position, initial hole. So you can see that the block has rotated by 90 degrees. Now we have to cut the second face of it in a similar manner. So now the second machine also machine the third surface and the fourth surface also. Means again we need to move it by 10 complete revolution of the indexing crank. Again this will revolve by 90 degrees, and the third phase we will machine it accordingly. See, again it is being revolved by 90 degrees. See, 10 complete revolutions has been done. So, see, the third space is being machined. See, so the third phase is complete, and the final phase we are machining it. So basically you have to repeat the process. The process is same, exactly same for all particular sites. Just you have to repeat the process, same process. So now the fourth phase is also machined. So you will obtain a completely equal sided square. So this is the actually the key. See, the square geometry has been formed, which is exactly similar to the required design. Now what we will do, we will make a hexagonal feature just at the opposite end. So we will fix it upside down like this onto the chuck, and see, it has been fixed onto the chuck. Now we'll make a hexagon in a similar manner, just like the square we have done it. Okay. So you have already calculated how much depth of cut we need to give. That is 2.01 mm. So in a similar manner, we will have to orient it accordingly. Okay, and we'll have to impart the depth of cut, and then we will have to move the job. So in this case, how much rotations do we need to impart onto this crank? 6 complete revolutions, and then after that 20 by 22 holes. Okay, they will show you. See, various types of number of holes have been marked onto this one. So one of the radii has got 33 holes. If you see this particular, it has got 33 holes. The top it has got 51, then 45, then 33, then 27. There are that means at various radii it has got the number of hole changes. Okay, so this indexing crank and the indexing pin has been fixed to the radii where it has got 33 holes. Okay, so we will multiply this 30 with the 2/3 fraction that we have obtained in the while calculation. That means 40 divided by number of sides that is required, that is 6, becomes equal to 6 complete revolutions and 2 by third of a complete revolutions, which means 6 complete revolutions and 22 number of holes, right, as I've explained previously. So you have to count the number of holes and then you have to fix it at the 22nd hole. So the starting side has got no issue. We can cut the first side. Then for the second side, we need to rotate this particular job by 60 degrees. So this DRO is especially the digital reader is basically you can find out how much rotation you are giving, because by manually you cannot judge how much you have reached. Okay, this is basically the depth of cut that they are giving. So you cannot calculate it from here. So you have to have a digital, feedback of how much have you moved. So this is the distance that they are moving. This is the depth of cut. Okay, it's 2.03. So now they will start cutting in a similar manner, just like the previous one. So the first side machining has been completed. Now we have to rotate the job to cut the second side of the hexagon. So we take it outside and then we have to rotate, because if you rotate over there, then there is a chance that it will strike with the cutter again. So we have to trace it back, then we have to rotate the job. So they will do 6 complete revolutions. Yeah, 6 revolution is complete. Now by 22 holes they have, and they have fixed at the 22nd hole. They have marked it previously with a chalk so that they can identify the locations. Okay, so it has been rotated by. Now they will be cutting the second side. Now second phase is complete. Now they will go for the third part. So how they will do? This is the starting position. This will act as a starting position. From here we will do 6 complete revolutions, bring back to this, and then 22nd hole is over here somewhere. See, 6 hole is complete, 6 complete revolution is complete. 22nd hole is here, over here. Okay. So the third phase we are getting. So this is basically the chuck key that has been used to lock the particular.
Sir, your video is not
Sir, your
Sir,
screen is
last
not
part
visible,
of the
sir.
video was not visible. Something went wrong.
Video was not visible.
Last 2 minutes, sir. Yes, sir.
Last two.
Yes,
Last
sir.
2
Okay,
minutes.
okay.
Screen is not been
Fine.
shared.
So something has happened again. It seems. Okay, I'm again starting the video. I hope you can see the screen now.
Yes, sir.
Yes,
Yes,
sir.
sir.
So the last part. No. So this is the hexagon that they are doing. Okay, 2 phases have been completed. So third phase they will do. So from here they will do 6 complete revolution, and then after that, with respect to this position, 22 hole, which is somewhere located over here. Okay, they are rotating it. Now this is the 22nd hole. Okay, they have fixed it over here. Now they will do the third phase. Okay, and accordingly all the 6 phases can be done. So this is the hexagonal site we have obtained by machining, which is perfectly the geometry that we needed to obtain. So basically, this is the chuck key that has been used to lock and unlock the the circular object onto the chuck. This is a 3-jaw independent chuck basically. So this is the completion of the video. Now I'll show you another animated video where you will witness the up milling and the down milling, and also the various types of milling operation that can be obtained using different kind of tools.
Sir,
Yeah.
sir, please can you explain why we use the radius with 33 holes?
So, because it is, you can multiply it with 2/3 fraction. It will lead to a whole number.
Oh, okay, sir.
Sir,
Otherwise, we can use any radius.
Yeah, accordingly. Okay.
sir, so
Let me
according to
stop
the
it.
number of sides, we decide the whole number. If
Yes,
there are
obviously,
okay.
because if you suppose, for example, you have n number of sides that you require. So what I have told you, we have to divide it by means 40 divided by n. So it might result in a whole number or a fractional part as well. So what you need to do for converting the fractional part into a whole part, you have to multiply with the number of holes. Okay, in such a manner that it will result, the fractional part will be converted into a whole number, right? That is why there are numerous number of holes that is available. Means it is there. Okay, so that there is a maximum chance that you will always get a complete whole number. Okay, in case of 2/3, you can multiply with 33, so that you will get a 22 whole number. Okay, and if you get say
Excuse me,
any
sir.
other fraction, yeah,
We can use 15 for that matter also. Is
15,
33
yes.
compulsory?
No, it is not compulsory.
We can use
In
15
that
also.
particular indexing plate, there is 33. There are 3 kinds of indexing plates similar to that. Okay,
Okay, sir.
each having different kind number of holes. Okay,
Any multiple
as
of
I
3
have
can
shown
be
the
used.
yeah,
Any multiple of 3 can be used.
yeah, why not?
Sir,
Not any
but
multiple
if,
of 3, any multiple of 3 in this particular fraction. Okay,
Yes,
if
sir,
the
yes.
fractional part is suppose 2/4. Okay, or 2 by 4, 2 by 5, suppose, let us take.
Multiple of
Can
5.
you multiply it by 33? No, obviously you will multiply it by 25, okay, or 50, or any multiple of 5, so that it results in a complete whole number. Okay, so if you have that many number of holes in a particular indexing plate, you will locate the indexing pin at that particular radii. As simple as that.
Sir, how did we decided the vertical depth till which the square or hexagon was cut?
Vertical depth. So there was a lever at the bottom by which they were lifting the work table. Okay, there is no particular depth that has to be maintained, but it has to be made sure that too much force is not imparted onto the tool. Okay, so normally what is done, if we require a pretty large depth, a pretty large deeper cut, so what we do, we don't do it in one pass, in one go. We normally do it in 2-3 passes. Okay, generally we do not cut too much in one go. Okay, because it might damage the workpiece. Oh, workpiece means the tool. Okay, it might damage the teeth of the tool. Okay, so generally what we do, when we require a very large depth to be cut, so we generally do it by more than one pass. Okay,
Yes.
that Z height is is adjusted by the operator by his experience, that okay, now my tool can handle this much load, opposing load. Okay, I can do it. Okay, if it doesn't handle, then he will give lesser Z value. Okay.
Yes.
Okay, now
Sir,
we
in
will
the,
yeah.
so the depth of cut is set by a means turning thing at the bottom, and the reader only reads it. Digital reader only reads it.
Yeah.
But
Digital
we
reader
cannot.
only just measures how much work table it has moved. Okay.
So it is not
So
not in the
basically there is a
reverse that
sensor.
we have to set it on the digital reader, and automatically depth of cut will be set.
No. You have to do it manually. Just the digital reader is there to assist you. Okay, that how much, because by manually you don't know how much it has moved. Okay, there is nothing precise reading that is there in the machine. Okay, so you need to have a digital reader for that. Okay, like just like you are riding a bike. So while riding, do you know how much speed you are going? You need to have a meter for that, right? A digital meter to be more precise, and an analog meter is there to give you an assumptions. Okay, so you need to have a reader for that. Okay, which will read how much you are going actually, because by manual sense you will never come to. Okay.
Sir,
Understood?
Yes,
sir,
sir.
when we counted the number of holes, that is 22 holes, so that was means we started from the first hole and kept on counting in consecutive integers and reached there and marked. Is that what we
Yeah.
did, or there are markings?
Yes, exactly.
Okay.
We just counted by 1, 2, 3, 4 like that. We counted the 22nd hole we fixed. Okay.
Okay, sir.
Sir, why lathe machine can't be used for cutting?
Cutting what? Yeah, cutting flat surfaces.
Yes, sir.
Yeah, it cannot be used in cutting flat surfaces, because what happened? How is the motion in a lathe? You have to rotate the workpiece. Okay, it always rotate in a axis, in its axis. Okay, circular axis. So can you hold, first of all, can you hold a flat kind of object in a lathe? You cannot. Okay, and even if you do it, how you will machine it without movement? Because you can only move the tool in either in a linear direction or in the radial directions with respect to the chuck. Okay, so how can you cut a different kind of geometry? You cannot. You can never cut. Okay, it will only have a relative motion if you have a circular kind of piece, so that you can impart a rotatory motions. Okay, if there is a flat kind of object, even if you have some holding device and you impart the rotatory motion, so obviously it will just bang onto the tool. Okay, the tool will break. Okay, just imagine what you're speaking. Okay, understood. Okay, let us understand by this animated video how we do different type of milling, like up milling, down milling. various other milling operation by using various other type of milling cutters. Okay, please pay attention. Here you don't require any sound. Okay, it is everything is written or shown in animated video. So this is specifically the up milling operation that is being shown. This green arrow is the feed motion of the workpiece, and this green arrow is the anti-clockwise motion of the tool. So these are the chips that is flowing out, okay, in bits and pieces. Now please observe over here, this is the end milling cutter. So this is fixed generally. For this type of cutter, we use vertical milling machine. Okay, not horizontal milling machine.
Excuse me, sir.
Yes.
So in the previous one, what actually was the use, sir? Because previously it was a flat surface and again we are making it flat?
No, previous surface was flat, okay, but it was a circular geometry, right? Say it was a cylinder. So our job was to convert that cross section, circular cross section, into a square cross section, and on the opposite side a hexagonal cross section. There is no particular application, just to make you understand how the milling operation is done, okay, and how a feature is generated, and how we are using the indexing operation. That's it, nothing else. It has not got any application that of a circular feature or hexagonal feature anywhere. We will not use it anywhere. Just to make you understand how the indexing operation is done and how the milling operation is performed. That's it.
Sir, not in that one, sir. In the say in this animation part.
Oh, yeah. Yeah, which one?
Sir, in that one where a cuboidal piece was there, and with the help of something like drill bit which was given, and the previously faced.
Yeah, this one you
yes,
are
sir,
speaking
this,
of, right?
exactly.
So this is called as an end milling cutter. Okay, so it can cut a drill also. Okay, it can drill a material also, or it can cut the edges also. So it has got a cutting edge at this end also. While by rotation this way, it can cut the face of a particular part. So sometimes what happen, we do not obtain a completely flat kind of geometry. It might have an uneven kind of surface. Normally it does have. So how we'll make it a flat? Okay, so we can do it by this particular machine. Okay, although there are specific machines to make a flat kind of geometry, there is a shaper machine also, which is dedicated to do a flat kind of object. Okay, but this milling machine is a very versatile one. Okay, as numerous kind of cutting tool can be fixed with. So in this machine also we can do the flat object by using the end milling cutter. By the help of this cutter, we can drill also. Okay.
Sir, can we use
Yes,
the
sir,
milling
got it.
machine
Thank
to
you.
shape a flat surface into a curved surface?
How can we change a flat surface into a curved surface?
Can we do that using milling machine?
Yes, obviously, but you need to change the tool in that aspect. We need
What
to
tool
have
is
a form tool in that aspect, which has got an opposite replica of the curved part. Is that has it been shown to you? Not been shown. Okay, you can understand it from here somewhat. Here, what happened? There was a requirement of having some, this round kind of what do you say, tunnel kind of thing, which has got a round cross section. How you will obtain that? Okay, so you need to have that kind of tool. See, this tool has got a circular kind of cutter, by help of which it can cut. See, yeah. See, this tool itself has got a circular kind of shape. That is why this kind of shape. Now, if you're talking about how you will evolve, a shape which is bulging outwards. So in that case, we have got a form cutter that I have shown in the presentation. I'll show it again. Okay, in the PPT it is there. That kind of form cutter is there. So, okay, which is dedicated to do a specific type of geometry. Okay, those all are known as form cutters. Okay, just like for example, we need to have a slot which is T in shape. Okay, we're gone. Yeah, see, we need to have a T slot. We need to make it inverted T out of here. So we have made a vertical slot, and then by using this type of milling cutter, see the cross section is T in an inverted T. Okay.
Sir, in down milling machine, sir, can you please show the down milling once again?
Yeah. Animation, are you talking about?
Yes, animation, sir.
Okay, fine. Okay, this is the up milling. Yeah, this is the down milling.
Sir, if we want to stop in the middle, there will be a curved edge like that, no, sir?
Yes, exactly.
Sir, we have already made the square shape, no, sir? In the video you have shown.
Yeah.
Sir, in that case, we should, the edges should be curved, no, sir? How we got the flat edges like that?
Because we have not stopped in the middle.
Sir?
Okay, if we have stopped in halfway, then we would have got a curve. guys?
Sir,
Okay.
but we cut up to some millimeters only, no sir. We have done the milling up to some millimeters itself only, no sir.
No, we have cut it completely. Means the job has been passed completely. Means one side has been cut completely. Upmilling has been done completely. If it would have stopped at half the length, if we would have stopped at half the length, okay,
yes,
and then again retraced back the job, then we would have got this kind of curve type of feature in the middle.
Yes, okay. I've got it.
Okay, got it. Fine.
Yes, sir, I've got it.
Okay, fine. So was there somebody asked about the form milling cutter, right? And let me show you. See,
Sir, how are these cutting
who was
tools
asking about the
better?
form milling cutter? How we can obtain a circular kind of feature?
I was asking.
Oh yes. See, now here you can see. So we will use this type of form cutter basically, which has got a curved at opposite side. Okay. So it will just form a replica of that. Okay. Have you got
We
it?
can use this to make a cylinder from a cuboid.
From a cuboid, yeah, on the not a cylinder.
We can do it on both sides, and then we can make a cylinder.
Yes, if you can hold that. Okay, but it will be difficult to hold.
But using this tool, we cannot choose the radius of the bulge.
No.
That facility we don't have.
No, because the radius of this or the diameter of this form cutter is fixed.
So how to solve that problem?
If you have to manufacture another form cutter for that.
That is very expensive, sir.
Very expensive.
Do
Yes,
we
that
have
is
any
why
dedicated machine for that?
No, in this only we can have it. Yeah, for making such type of particular geometry, there are different machines for that.
Okay.
Like for example, I've told about the gears. Okay, to manufacture gears, it can be manufactured by here in indexing, but it will not be that much precise. So it has got dedicated machines for that to making a gear. Okay, a helical gear or a straight tooth gear. There are dedicated machines known as gear shaping machines. That is known as gear shaping or gear hobbing machines are there. Those are also machine tools. Okay, just like the milling machine, but it does only gear operations. It can manufacture gears. Okay, with high precision.
Sir,
which is not achievable in this milling machine. Yes.
Sir, how are these cutting tools made? Means from these only machines, milling and lathe machines.
These cutting tools are made by different type of machine tools. Okay, there are CNC machine tools which can make, or there are specific molds by which it is made. Then it is grounded to get the edges. Okay, there are various processes. It also depends upon what type of material we are using. Sometimes ceramic material we are using, then it becomes very tough to machine it. Okay, so if you are using HSS, then also there are different processes to obtain. Okay, so it is pretty much difficult to make this cutting tool. That is why these are very expensive. Okay, these cutting tools are very expensive. That is why while machining, we need to take care that we don't damage the cutting tool. Okay, because if one teeth is damaged, then we cannot use it. Okay.
Sir, can we make a cylinder from a cuboid using lathe?
Using lathe, a cylinder to a cuboid?
Yes.
No, we cannot.
So the square that we had made on one side of the cylinder, so in that, at the base of the square, the thickness of the material removed, and at the top of the square, the thickness of the material removed will be different, right?
No, why it will be different?
So because in down milling or up milling, both cases, the thickness of the chips removed are different, right?
Thickness of the chip removed are exactly same if you notice the chips. Okay, but the way it is being removed, I told. Okay, different. Okay, if you see the chips individually, it will look exactly similar. Okay, if the same feed motion and the same RPM is there of both the machine in both the processes. Okay, the chips thickness is exactly similar. Okay, but while we are doing the machining, what I have told the difference is that while in motion, the chip thickness gradually increases in case of upmilling, and in this case gradually decreases. This is what I have told. Not that these two chips are of different dimensions. Okay, if we keep the feed rate and the RPM of the cutter exactly same, it will evolve the same dimension thickness. Okay.
Thank you.
Understood now?
Yeah, understood.
Okay. Any further problems?
Yes,
Sir,
sir.
can you
I
please
have
do the
doubt
example
in
video
depth
again?
of cut.
Yeah, one by one.
So can we have varying depth of cut on either side?
Yes, why not? But what is the use of that? If
So
there is
like
specific
there might be
design
a specific
required, yeah,
shape.
there might be. We can have it because the depth of cut is manually given. Okay, we can have different depth of cut. Why not? Okay, but
Sir,
yes, but
can
here
you
is the catch.
explain once
Yeah,
again how is
wait,
depth of
just a
cut
minute.
controlled?
Depth of cut controlled. Okay,
Yes,
fine.
how we set
Yes.
it in the machine, that's a doubt.
That there is a lever. Okay, at bottom, yeah, in this knee there is a lever by which Z movement can be controlled, and here is the handle in which this in this case Z in this direction. Okay, so there is a two separate hand wheels are there by which one can control the Z motion, means a vertical motion. One can move this horizontal motion in this way. Here it is Z direction. Okay, so this motion. Okay, there are two separate hand wheels by moving of which we can give that motion accordingly. Okay, now who were asking about the depth of cut, let me tell you. Okay, if you have a requirement of two different depth of cuts, you have to make sure that if the depth of cut is pretty large, then we cannot give it at one go. We cannot make that depth of cut in one go. Suppose somebody asks you to give a depth of cut, suppose let us take 15 mm, okay, which is pretty large, 15 mm. It is not advisable to go to make it in one go. So what we will do, we will try to make it in two passes. Okay, so if we require two separate depth of cut, suppose one we need a 5 mm depth of cut, another point we require a 15 mm depth of cut. So in case of 5 mm, we can do it in one go by giving a 5 mm depth of cut. But in case of 15 mm, we cannot. We have to either do it by two passes or three passes, depending upon the cutting tool strength and the workpiece strength.
Sir, it is similar to the step turning.
Yes.
It is similar to step turning.
Exactly similar to the step turning. The logic is exactly similar. Okay.
Sir.
Now, what occurs actually? What is the problem that occurs? The same problem occurs in the lathe also. That when we give a massive depth of cut, basically what happens? The intimate contact length between the starting of the cutting tool till where the chip is in intimate contact, that length increases basically. Okay, and thereby the mode is the depth of cut. The mode is the opposing force as well, opposing frictional force on the surface of the cutting tool. So mode is the frictional force. Mode is the heat generation. Okay, more the heat generation. So it might try to soften the edges of the cutting tool. Okay, that might blunt the cutting tool. Or if the cutting tool is very hard and brittle in nature, so the opposing cutting force will be, if it is quite large, then it might lead to sudden crack of the cutting tool tooth. Okay, it might completely break away the cutting tool tooth. Okay, so it is a similar thing in just like plate. Okay, the logic is same. Why we don't give a large depth of cut?
Excuse me, sir. Yeah. Sir, how is it in down milling that the last part becomes completely flat? Because
okay, this part down milling, how it becomes
how
completely
it
flat.
at the end, how it becomes completely flat? Why? How is there not means a bulge remaining?
Okay, so this tooth is just the side view that you are seeing. It has got some width also. Okay, in the inside part it has got some width also, and that is completely flat. Okay, so that part is means this cutting tool has got a thickness to it also. You are just viewing the side view of it. Okay, it has got a particular thickness, and the cutting tool edge is completely flat. Okay, so when it will chip away a particular material, it will just move. Let me show you. Yeah, it will just remove a chip in the form like this. My drawing may not be that good, but bear with me. Yeah, like this kind of chip will be removed. Okay, so if you see, this edge is completely flat. Okay, so if this is the workpiece, suppose, so till here it will have a different, sorry, ignore this part. So this height is more, and this height is just the cutout height. Means this particular height and this height is different. Okay, if this height is capital H, I'm talking about this height. This height is small h. Okay, and this height which has been cut out, this height is actually h1 with respect to this angle. Okay, did you get it now? Yeah, whosoever was
yes,
asking, did you get it?
Yes, sir. Got it, sir.
My drawing may not be that beautiful. Okay, and it is very difficult in this online mode. Okay, I hope you have got it, right?
Yes, sir.
Okay, is there any further problem? If you have, now this PPT and the video will be shared to you, okay, in this MS Teams, so you can, if you have any doubts regarding that, you can see the video once more. Okay, and if you have any further doubts, you can just text it in the MS Team. We will deal with it. Okay.